In this video, I'm going to talk about rotational kinetic energy. As normal, I'll start with a bit of theory, and then I'll give some practice examples at the end. Please take a moment to read the success criteria I plan to cover. So just like the other videos I have in this section for rotational motion, let's go and relate our translational motion or linear motion and rotational motion, because we already know this, and as long as we can, in our heads, just go from one language to another, linear to rotating, we already know how to use these equations. Kinetic energy is exactly the same, and if I'm moving in a straight line, I have mass and velocity. This equation here just has its momentum and its mass. They're just two forms of the exact same equation. But if I'm rotating, it's not just the mass that's important, it's the moment of inertia, or how that mass is distributed. So that's what I need here instead of a mass. And instead of just my linear velocity, I now have an angular velocity. So this equation here is exactly the same as my first one here. And for the second one, instead of linear momentum, I have angular momentum. It's not mass times velocity, it's moment of inertia times angular velocity. And on the bottom, 2 times moment of inertia. So if those are the same, conservation of energy is still going to be exactly the same as before. If I have a box, we would have our box sliding down our inclined plane. And at the top here, we had gravitational potential energy. And then it would be translating all that, or transferring all of that into kinetic energy at the bottom. So let's take a look at this animation I have here that I made in Algodoo. I've got a box on an inclined plane. And at the side here, you can see that I have a total energy of 8.761 joules. And as the box starts to slide down the ramp, you can see that it increases the kinetic linear energy, and the potential energy decreases. Now, if I have a ball or a sphere, as it goes down, it's going to take this gravitational potential energy, and we know it's going to start to move, and I will get kinetic energy at the bottom, but now some of this will be linear, just like with the box, but also now I'm going to have some that's rotational, because it will be rolling as well. So now let's watch the ball roll down the hill. You can see I've started with 10 joules of energy, and it's gone into both kinetic linear energy and also the kinetic angular energy, or rotational energy that we've been talking about. How are we going to have some differences? Well, in this case, it's all going to be 1/2 mv squared for our linear kinetic energy. And in this case, I'm going to have my 1/2 mv squared, as well as my moment of inertia times the angular velocity squared. Now notice, if this box is going to slide down, it's going to be at then a different speed than the ball rolling. Why? Because some of the energy has to go into making it roll. And now, just like we had the differences between the box and the ball, if I have a sphere that is solid compared to just a hollow sphere, they are going to have different moments of inertia. So in the IB, you don't have to know these equations. They're going to have to give them to you. And in many other different curriculums around the world, they might be in a data booklet as well given to you. So for a solid sphere, someone's done the calculation for us about how the mass is spread out. A lot of fun calculus involved. And the moment of inertia is found by 2/5 times the mass times the maximum radius we have of the sphere. For this shell, now all of the mass is going to be just at that one radius, and it's 2/3 mr squared. You can see here that the thin shell has a higher moment of inertia. Why? Because more of its mass is at a greater radius. In the sphere, we have some that is closer into the center. So here I have a one mass circle sliding down our ramp. And now I have a one mass ring sliding down our ramp. And let's take a look. Yes, they have the same mass, but they have different moments of inertia. The ring, which has a larger moment of inertia, ends up getting a larger amount of rotational kinetic energy, and in the process then will have a lower amount of linear kinetic energy, which means it will have a lower linear speed. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. Okay, so let's go through an example. I have a solid cylinder here of mass of 2 kilograms, length of 1 meter, and radius of 5 centimeters, and it's rotating at 3 radians per second. And I'm asked to calculate its rotational kinetic energy. But in the first part, it's rotating about its center axis, like this picture right here. Now, in this case, you can see that our moment of inertia is 1 over 12 mass times its length squared. So for kinetic energy, 1/2 moment of inertia times its angular velocity squared would give us 1/2 times 1 over 12 times 2 times 1 squared, and the angular velocity is 3 radians per second squared. This is a good time to mention that in this case our angular velocity must be in radians per second, not revolutions per second. So if you ever have a question that has revolutions per second, you will have to convert the units. Now if I pick up my handy dandy calculator, I will get 0.75 joules. Now in part B, it says it's rotating about one end. And in this case, I have a different moment of inertia. If you think about it, the mass is spread out differently. In this case, the mass at most was 1/2 L away from the center of rotation. In this case, well, that would be the average. Some of my mass is now a whole meter away rather than just 1/2 meter. So now my moment of inertia is 1 over 3 times the mass times, it says here, the length, which is 1 squared, and the rate is 3. Again, picking up my handy dandy calculator, I get 3 joules now of kinetic energy. If you think about it, this one, as I said, it has a greater moment of inertia. It should have more kinetic energy. I know if I was going to get hit by one of these two, I think I'd rather be hit by this one than this one. Why? This one doesn't have as much kinetic energy. Okay, let's do a little bit more of a complicated example. A solid disk of radius 0.25 meters and mass of 0.5 kilograms starts from rest and rolls down a ramp of length 4.5 meters. The ramp has an angle of 15 degrees, as shown in the diagram. Well, now I have a diagram. And for a disk, here is how we calculate our moment of inertia. What is the linear speed of the disk at the bottom of the ramp? Well, we know at the top it has potential energy, and as it goes down, my disk will roll, and the gravitational potential energy will be transferred into both rotational and linear kinetic energy. So let me set up my conservation of energy equation. I have gravitational potential energy, and I'll have linear kinetic energy and rotational kinetic energy. mgh 1/2 mv squared 1/2 I omega squared. Now, the height will be here. This will be opposite and hypotenuse. That would be 4.5, and that will be sine because it's opposite and hypotenuse. Sine 15 degrees. 1/2 mv squared. My I right here, 1/2 times mass times r squared times omega. Now I don't have my angular velocity here, but we do know that velocity is the angular velocity times the radius. So I can move this around. This would be angular velocity will be v over r, and that is all squared, which is good. So that will cancel out here and here because of the square. mg 4.5 sine 15 Okay, so notice here, first of all, my m's will cancel out, which typically does happen when we have conservation of energy. And I have 1/2 here and I have 1/4 here. So together I have 3/4 v squared. So if I've got 3/4 v squared here, I'm going to move it to the other side, which will give me 4 over 3. I'm just going to move from one side to the other. 4 over 3. And this is going to be end up with under the root sign because I want to get rid of that. G is 9.8. Make sure your calculator is in degrees. I pick up my handy dandy calculator and I'm going to get 3.9 meters per second. That will be my linear speed of the disk at the bottom of the ramp. Now for the last part, what's the final angular velocity? I'm just going to use this equation again right here. My angular velocity will be that v over the radius, 3.9 divided by, my radius was 2.25 meters, giving me 15.6 radians per second. So please take one more moment to read the success criteria. I hope after this video you can say yes to all of those. And if you liked this video and it's helped you out, please hit like, perhaps subscribe, tell your friends. It really does help out.